All right, you ready for some grade A nerd shade? This diagram shows a bunch of comparisons of different algorithms, and the authors say, we do not plot for Merkle-Tri as its overhead is significantly higher, over 40, than the rest. You gotta love it when you're comparing yourself to 6 other algorithms and you leave one off because it would make your chart look not so great. But, you know, this is a lot faster than that algorithm, and so maybe they have a reason to throw shade. So let's get into it. Today, finally, we are talking about practical rateless set reconciliation. This is the juicy stuff that I really wanted to get into. This is part 3 of a 3-part series on bloom filters. We started at the beginning with, hey, what is a bloom filter? How does that work in general? Then we moved up to an invertible bloom lookup table or invertible bloom filter. And that got us some of the sort of foundational principles that we need to understand this paper. This paper is from February of this year, 2024, and it's super fun. We sort of saw in the last one that we left off with this kind of womp womp moment with invertible bloom filters, where you needed the set difference to be kind of known on both ends of the wire before you could use it meaningfully to do the inversion and the set reconciliation. This paper gets rid of that, which is wild. And the way they get rid of that is, it's fantastic. So let's get into it. And first, I think it's worth just starting off with like what we're trying to do with set reconciliation as a beginning point. And so as a trivial example here, we have Alice and Bob, and they have 2 sets, A, B, C, D for Alice and B, C, E for Bob. What we want to do is reconcile those. The idea here being that all of these elements that are single letters are kind of items that we need to eventually end up where Alice and Bob both have the same set of stuff. All unique messages are replicated on both sides. And so to do that, we're gonna do a reconciliation process. And so we kick that off with, hey, Alice says, let's reconcile. Bob says, okay, great, let's reconcile. And the 2 of them do something to get the elements they need on either side. Now, some stuff worth noting here. There's a naive way to do it. Alice just sends Alice's entire set and Bob just sends Bob's entire set. But when you're dealing in millions of items, that's super wasteful, particularly because you know that both ends of the wire have some elements from either set. And the authors kind of take a fun cut that I haven't seen before to this problem. They look at that and they say, well, that looks a lot like erasure coding. That looks like the issue of needing to understand that both sets contain errors and they need to be healed in order to arrive at a place where both places have a correct representation of the set. And that erasure coding sort of frame of reference informs a lot of this work and gives a really interesting sort of foundation for how they've kind of hacked into the structure of a bloom filter in general to come up with this rateless construction. And so with that, I think it's worth first starting off with just our basic listing of operations that are supported in both. So we left off, the invertible bloom filter gave us insert, delete, get an element, and the fun one, which was list all the elements in the filter. And to do that, we had to do the find a pure cell, and there's very specific characteristics that go into that. For more on that, go watch part 2 of this 3-part series. A rateless IBLT, first and foremost, the invertible bloom lookup table models a key value pair. The IBLT models sets specifically, and so it is just dealing in a list of things. It doesn't do the key value stuff. It instead reserves that second part for a checksum, which is mainly for the use case of securing the values inside of the thing that you're reconciling. Yeah, I've listed here that to do is sort of check the presence of an item. That's because the paper doesn't even really bother implementing or talking about it. It's mainly concerned about this idea of reconciling over the wire and using the listing property to figure out what elements are in both sets missing from each. And so it could be implemented, but that's not really what this data structure is for. This is kind of purpose built for set reconciliation. And so just as like a review, when we looked at invertible bloom lookup tables or invertible bloom filters, we had this like lovely property where we can put stuff in, but it had this kind of downside that it was fixed, right? The actual width of the filter in cells is always going to be some preset amount. And if you change the width of that filter, those 2 things are not comparable. And you can recover stuff from it, you can put stuff into it, that's really great. But if you got into a situation where one end of the wire didn't have the right set size, you end up not being able to invert the filter. And a lot of the challenge comes in figuring out how to estimate the size of the set. So coming from this approach that the authors of this paper have come through with, they have a set of properties that they want to imbue on their variant of an invertible bloom filter that will hopefully help get rid of some of these characteristics. And so those three properties that they're going to shoot for in this piece are decodability. First and foremost, the whole point here is to arrive as quickly as possible at a bloom filter that can invert on the other side. And so what that means is you're going to take your bloom filter, you're going to send it over to the other side, they're going to XOR that thing, and you're going to ideally end up with a resulting delta bloom filter that can be inverted to get all the elements out. So decodability is kind of the whole purpose of this thing. Linearity is a very interesting property that we'll kind of get to in a second, but that basically says that for all elements in the set, we want to have a total order to the whole thing. And that actually is defined universally, which is the last and third property. Universality in this case means there are no additional properties or parameters provided to the bloom filter other than the set that you're trying to reconcile. And so that's a pretty bonkers set of requirements. Basically, what this is stating is for any possible element or set of things that you want to synchronize, it needs to, without any additional configuration, be able to establish a total order for that thing, get to a fast decodability, and do that without additional configuration, as mentioned. And so the way they do that is the prior invertible bloom filter stuff looked at, called these items cells. They're now calling them coded symbols, which is sort of the things that the items are going to map to. So in our cells construction, we had a fixed set of cells, and these are now going to be a sequence of coded symbols. And those coded symbols are infinite. And this is where the rateless part comes from. And this is kind of weird to get your head around. But in this case, if we had a set with A, B, C, and D in it, the amount of coded symbols you can generate from that set can go forever. Which feels weird, but you'll see why in a second and how that's not actually what you end up doing in practice. But from the mathematical underpinnings of this, the set of coded symbols for just these four set contents for really any set, you can just continue to generate new symbols forever and forever and forever. And so there is no required width of a rateless invertible bloom filter because it's rateless. What ends up sort of happening in practice is this mapping, where every element is going to map to some of these cells, the same way that you would in a regular fixed width bloom filter. But if you look closely at this pattern, you might already see something jumping out. First and foremost, every single cell always maps to the zeroth element. And then at some random probability, cells will map to fewer and fewer of those items moving forward. And we're gonna spend a lot of time digging in on that, but that's the core principle, and this is kind of why I call it left justified. Every single item ever will always map to the zeroth element, and then from that point forward, there is, with a degree of determinism, a decreasing amount. There's a decreasing probability with which any item will map to a given coded cell. And this is kind of how that looks in practice. There's a mapping probability, and a lot of the work of this paper is finding the sweet spot in this. So again, the whole thing we're trying to optimize here for is decodability. And so for a given set, if the probability falls off too slowly, what you're going to end up with is almost too thick of a filter, right? Remember, we're hunting for that pure cell, a cell that has only one element in it to initiate the peeling process in the beginning. And in a rateless invertible bloom filter, you know you're finished when you can peel the zeroth element, because every single element is mapped to the zeroth element. So if you can get the zeroth element to be empty, then you know you're done, which is a very cool trick. But if you get that probability descending too slowly, you're gonna have to go for a long time and you're gonna have a lot of overhead before you by chance encounter a pure cell. Conversely, if you descend too quickly, you're gonna have a bunch of empty cells and basically kind of pack everything into the zeroth element, and there's a very real chance you won't be able to decode the thing at all. So the authors put a lot of time into figuring out what the right slope of probability is here. One last thing to state here that I think is a little bit counterintuitive before we move on is that this is a decrease in probabilities, not a decrease in mappings. There is a technique that will say for any given element, it will assign a different, it will establish a different side of that probability. But this isn't saying that every single element is going to map to the 0th and every single element is going to map to the 1th. This is saying with 100% probability, every single element is going to map to the 0th. Yes, that's true. But with 82% probability, everything is going to map to the 1th cell. And with 64% probability, everything is going to map to the 2nd cell. And that is a probabilistic thing. You intentionally don't want every single item to, you want to just take every item and say, you know, whatever, let's take the whole set and take 40% of them and have them map. There has to be a lot more sort of thought and care into how different elements get mapped to this thing. And that's where the linearity property comes in. And so we'll get into that in a second, but this is kind of, the important thing to note here is this is a slope in probabilisticness. Super technical term. Anyway, the second thing that they have to do is figure out how to do this efficiently, right? So if we can consider that given a specific set, we want to be able to have the right number of elements mapped to each thing with this probabilistic curve and decrease. But the naive approach would be to say, take every element in your set and then go iterate every symbol by every element. And you can see how this would get really computationally expensive really fast. And so the second major contribution to this paper is an approximation of how to, given any element, turn the provided element into sort of this generator of the next thing, the next cell that any given value will map to. And so the authors come up with this formula, which is, showing math on the screen doesn't really help a ton, but we'll sort of get into that in a bit. But I think what is useful and worth noting here is what comes out the other side of this is a generator function. And for that, it's worth just looking at how we would build one of these rateless invertible Bloom filters. And so with a set, we're going to have the items 3, 2, and 8. And again, we're working with numbers here, but it's general to any data type. You can really do anything that'll map to bits, which is all things in computers. So we Gucci. But instead of having a set number of hash functions like we did before, what we're now going to replace that with is a generator function, a set of generator functions. And there's going to be one per item in your set. If that sounds expensive, that's where the work of this was, to generate a very cheap formula for approximating the next index for each of these things. And so these little sort of like generator function things are actually quite small in terms of the amount of state that they have. But the important bit is when you call them, they tell you for a given element what the next index in the infinite sequence that item would map to. And it is important that the randomness of that mapping follow that probability curve. You notice here we don't actually have any data on the screen yet. And that's actually kind of on purpose, because we can do these mappings. And again, it is worth noting that the filter itself is rateless. And so the width of the filter doesn't really matter here. So we can reset all of our mapping functions to 0. And then we can sort of just like keep in mind that this filter is going to be whatever width we need. And we're going to use these generator functions to figure out what of our set needs to go into each cell to construct the filter. What you end up with in practice is something that looks kind of like this, where you're going to have a deterministic relationship for every element that goes in. And that is then going to map to specific cell spots. The way that deterministic relationship is formed really, I thought, was delightful. The way they do it is they take the value that you're trying to map and they use that as a seed to a random number generator. And then they just call that repeatedly. Isn't that a lovely method of sort of establishing deterministic randomness? It's like such a lovely thing. So you take your value, you jam it in, you create a random number generator with that. It's deterministic because the seed you fed it is the value. And then you apply that probabilistic sloping decrease function and use the fancy algebra that we don't have time to get into to figure out how that is going to estimate the next cell. And you get this. And the authors have sort of gone to great lengths to prove out the theory behind that. There's a lot of deep probabilistic theorem proving here that is not going to jam itself into a 15-minute YouTube video. And so I'll leave that as an exercise to the reader who's deeply interested. Instead, what I think we should look at is how this works in practice when we actually go to reconcile over the wire. And so again, let's go back to Alice and Bob, but this time we're going to look at two sets. Alice has A, B, C, and D. Bob has B, C, and E. And now this time we actually have each of our coded symbols all prepped up. I'm not going to show the preparation of the sets, but you now know that you're going to generate a set of coded symbols each. And so what's going to happen is Bob's going to say to Alice, hey, I want to reconcile. And Alice is going to be like, great, let's reconcile. And so what Alice is going to do is Alice is then going to start sending a stream of each symbol. So on Alice's side, she starts with no symbols generated at all. And just as she's sending the first one, she comes in and says, okay, cool, I'm going to generate one, sends it over the wire. Bob's doing the same thing on his side. And then what Bob is doing that Alice isn't doing is Bob has both sets. And so Bob is actually XORing each cell as it comes through. And what's neat about that is as long as both sets are the same length, the paper calls that a prefix of the infinite sequence. And that is just like a regular invertible Bloom filter. You can XOR it and then you can try to decode it. And this is the magic of the whole thing. You have now a Bloom filter that can grow one element at a time, and that gets sent over the wire, and Bob just tries to peel it. And the second Bob can XOR them both together and peel the XORed result, he knows he's done. And so what this does in practice is this removes the need to estimate the difference between the sets, because the sets are being generated because the filters are dynamically growing until the moment that they don't need to grow anymore. And that's built into the wire stream. I think that is a beautiful way of skirting around the issue of figuring out how to size your filters. Just make the wire format size the filter until it's as big as it needs to be. And what the authors arrive at is this process ends up being generally between 1.32 and 1.7 the times the amount of the difference between the sets in terms of data overhead over the wire. So if you had 2 million items in Alice's set and Bob's set, and you reconciled them, but there were only 5 elements that were different between the two, you would have to send those 5 elements times 1.3 over the wire. Isn't that a ridiculous, it's an amazing piece of work. And the thing that is really cool about this is these sets are universal. And so the set and the symbol set that Alice has generated for this set, for Bob, can be completely used for someone else. It has no reliance on the state construction of any of the session-related information. Bob's set is universal to Bob's set, and Alice's set is universal to Alice's. And so once Bob gets this over, Bob now has been able to XOR them and knows that, okay, this is what I need and this is what Alice needs in order to be able to do everything. And if Bob's a nice human, maybe there's some mechanism for Bob informing Alice of what Alice needs to grab from Bob. But this is kind of the whole jam. It's a lovely, lovely, lovely improvement on the estimation of difference stuff. And it does that by really digging into the guts of the way that a Bloom filter is formed. Normally we rely on the uniform distribution of a hash function, and instead someone has done the hard work of figuring out how to make this sort of left justification and spreading that is just beautiful. The authors do note that PinSketch, that is the set reconciliation mechanism used inside of Bitcoin, is actually less data sent over the wire, but it requires a lot more computational overhead than this does. And this has this lovely property of, let's say Alice's set gets modified, it's relatively straightforward to then fold that new element into an existing Bloom filter set. That's the same as adding to one that already exists. And so between the sort of universality, the removal of the need for estimation, and the sort of general deep dive work on how to actually build out a Bloom filter that can grow one element at a time, I think this is a really exciting contribution to the world of bloom filters. And it was so exciting that it was worth going through and talking about 3 videos about it. And so I hope you found that as interesting and intriguing as I do. There's lots more to cover in this world. I think it's worth sort of like looking at some of the downsides of this before we part. As far as I can tell, I would like to see in practice just how big the overhead is for the construction of these things in terms of the maintenance of these mappings, right? It is worth noting that for every single element in your set, you do have to allocate one of these mapper functions. Is it that big a deal? I don't know. I haven't seen it in practice, but in looking through the code, it is really not a ton of memory overhead. It's the cost of the state for the next iterator plus a random number generator. So it shouldn't be too big a deal, but yeah, it's worth checking out. And I think the other bit that is worth noting here that all set reconciliation pieces sort of struggle with is a degree of transactionality, right? For the duration of this reconciliation, if the set that Alice is working on changes, that you kind of have to figure out some way to put a bit of a transaction lock around the reconciliation process and say, okay, pretending for a second that it's actually messages that we're let's say we're doing tweets. If Alice received a new tweet or generated a new tweet or changed her set in some meaningful way or in any way at all, then that can't really be added into the reconciliation process because that would throw off the construction of the whole thing. That, however, shouldn't be foisted on this mechanism in particular. That's kind of true of all of this line of work. The idea of dealing with the dynamism of that is just uncovered work or something that I haven't seen in the wild yet. But that's what kind of makes this so exciting. I think this is a process that presents a really interesting method for reconciling sets. And it's so interesting, in fact, that it makes me wonder about even harder problems that we haven't really figured out yet. So I hope you enjoyed that as much as I do. I would love to know if you have any other papers that are interesting. This paper was DM'd to me by Liam on Twitter. Thank you, Liam. It's so nice of you. Really appreciate it. If you have a paper you want us to cover, I would love to cover it. Otherwise, I hope you have a lovely day, and we'll see you in the next one. Thanks.